thing, and this is again, this is so somebody who just joined us today, it's fine. Like by just you following this with us, we will all be on the same page. So the first thing here that we did, we got the data from this data source that was provided. So we downloaded this. So it was a tar file that we downloaded. And then the tar file, of course, have many files, not only a single file. So we actually went to the CSV, and that's the one, that's our data set. So we actually were at that. And here, when we have head, we can just use, so head just shows the 5 top rows, but you can put here 10, or you can put anything that you would like to see, okay? You can even put here tail, you know, and we've seen all this. And then we went through the, okay, this is like, okay, why we did this? We said, okay, are there any, is everything numerical? Is everything numerical, or there are categorical variables there too? If there are categorical variables, so we want to know that because we want to deal with that, okay? And this is what this one is showing. So it's showing that everything here is float, except this last one, it's an object. And if we go, actually, if we check what's this object here, we're gonna find that it's a string, right? And that's what we found here. And then here we do the count. So what's this? So we go to this one and we say, oh, okay, so this one has 5 different categories here. So there are 5 different 1, 2, 3, 4, 5. So there are 5 different categories, and this is the total count per each category. Then we said, okay, so this describe tells us like more things, more insights that we can get from the data. And then we spent a good amount of time talking about histograms. Okay, and then there was there was a good discussion here. At this point, anybody want to add or mention anything about up to here? Okay, the camera today is here, so I want to get used to, it's not to my right now, I'm just looking at you here. Okay, any questions here? Okay, no. So then we went and we said it's very why setting the seed to a specific number is important. That way we can compare our runs. So we always have consistent results that we can compare. And let me just get the chat. So I'm following the chat. I don't see it. Let me just make sure. Okay. Chat. Okay, perfect. So I'm also looking at the chat if you're writing it in. After that, okay, after that we said let's create a test set, and then he did. So there were 2 ways how he did it. So this is like he wrote a function to split to create the test set. And then he also used the scikit-learn function to do that. And so here, so that's the function that he did. And then he specified, he says it's 20% test and 80% training. And this is the size of our training data set. So there are 16,000 rows and 512. And if we really want to know also like how many features we have, so there are 10 features, okay? And that's what we're looking at here. So these are selected. So there's longitude, or we can also here, if we just want to say so these are the columns that we have. Right, but we're not, so this is the one here, median house value. That's the label, that's the one that we are trying to predict, right? So we actually were using all this, the rest, and this one here is categorical to be able that next time when we get an unseen data points, here would be able to predict what's the mean value with a good accuracy. Okay, so let me then just run. So you see how here I haven't run this. So that's the point. I want to run this together. And then so, okay, the test set, that's the size. Here, you guys remember when we talked about the Hessian, right? You remember why he said it is very important to use a Hessian, and why is that? So that way, for example, when we add the new data sets. We said, for example, we have 1,000 data points, and then we add the 1,000 data points. For the test set, we still want to keep the original 20% that we took from the first 1,000 data points. If we don't hash them, and then let's say maybe we randomly again take a test set, then we may not have the same 20% that we had the first time. But because hashing will actually give us the same result of that identifier, we can just use that. Okay.
Salim.
Yeah, please go. Yes.
Yes. So in this particular function, I have a little bit of question. Now, when we look at this function, but the split trend test by ID, that's fine. But from here, it is getting called the above function, which is test set check. Now, the reason that you told, that is the exact reason. Like they are coming up with the CRC hashing so that they can check whether initially, if you go down, then you'll see that they are actually doing this hashing based on some identifier. So and the identifier which is not going to change. So initially they are doing this hashing based on the row index, and then going ahead they are coming up with computed column, and top of that they are doing that. My
Yeah.
point is that now when you are doing this hashing, it is understandable that for the same value, the hash value also going to be the same. So if also we introduce some new data, but for the existing data the hash values are going to remain same. That's how they are checking. The point of coming up with this function is that the hash value. So once we split the whole data set into test set and trend set, the intention of this hashing function is to ensure that any row that was previously there in the trend set, or rather in the test set, does not switch the party, right? So any row that was previously in the trend set, after this, the intention of this function is to make sure that any row that was there in the trend set in the new data set does not change the group to go into the test set. That was the intention. So now if we look into this function, the test set check, inside that when he is doing this return crc32 np.int64 identifier, that's fine, and this hex value less than this one. So how this checking, hash checking, is getting done, I'm not understanding. So here in this return statement, if we see, this only is going to give me the hash value of the corresponding row identity,
Okay.
where that is getting checked that this hash value is the same as the previous hash value.
Mm-hmm.
So it is just going to return as the hash value, but where is the checking that is getting done, that this hash value is the same as in the previous case?
Okay. Okay. So for example, here I did 50, right?
Right.
So let's say 50 comes from this our index. So let's say our
Right.
index is now it's 50. So right now,
Right.
but our data set is only 1,000. So maybe this 50 is gonna go all the way to 1,000. Okay, cool.
Mhm.
And this 50 will be part of our test set. Next time we added 1,000 data sets. Now we have 2,000. But we're gonna go to this 50. We're still gonna have the same hash value, even if we
So
have.
where exactly that cross checking is being done, that this is the, so how this hash value is being used?
Okay, so let's walk through this. So okay, so
Hmm.
here we get this, and then this is pretty much just a mask. It's just ending that, and then this is what we're saying. So this one is a 32. So the result of this is a 32-bit,
Hmm.
and then it says if it is smaller than 20%, 20% of this. This is the biggest value, right? This is what this is the biggest value, right?
So this is the second question I have. How, like, why is it biggest value on, like, from what perspective?
For, so for example, okay, if you have 32 bits, right? You have 32
Right.
bits. What's the biggest really value that you can get of those 32 bits? Really, it's 2 to the
Two
power
to the right.
32 minus 1. Or you
So
can just,
how come the bit thing is important here? Like, as you said, I also understood that it is 32 bit, but how come the bit thing is being considered here?
the bit, for example, this is 32-bit specific for this hashing function. So for example,
Right.
right? So for example, he can use a different number of bits, for example, but then he will have to change this. But I don't want to like go around circles around your question. But for the bits that just the one. So for example, like going back to that one, so he showed a different hashing function, right? The MD5. Let's see, what is that? Prepare. Okay, so it's here. So for example, this one. So this one is not a 32-bit. That's why here he has 256. So apparently this MD5 is the result of this one, and we can end here. Let's actually try that. But yeah, so I hope that clears some. So for example, if we just come, what's that? So okay, so if we do. So this is okay. So it's a hex value of 48. So 2 to the power 8. That's 256, right? Yeah. So this is at 250. So but again, it's the same thing. So it's always checking 20% less than that, and the values will always have the same number. So no matter, even if we add 1,000. 10,000, the 50 will always have the same value. Anybody want to add anything to this, maybe to clarify, to subsist the point?
So actually the confusion that I have is this test ratio generally we apply on the data set that we have. Why are we applying the test ratio on this biggest value like 2 to the power 32?
Why are we applying this?
So that you can compare, because CRC32 is going to give you a huge number. So if you get a huge number, you want to compare and scale it with something big. So when you do test ratio into 2 power 32, you get something which is as big as, if you look at the cell number 26, something which is of that scale, 27311892953. So an easy test for you to perform is if you change the test ratio and make it a smaller number, or a bit, you can make it bigger than this. But let's say you make it much smaller than this, then you'll see that everything is going to sit only in one set. Your less than is equal, less than sign is just going to pull everything into one data set. So you won't be able to technically split it into a train versus test set.
So why aren't we applying the test ratio on the data set, length of the data set?
You're applying, yeah. So you're, yeah, go for it. Sure.
Yeah. So the hashing function is just going to give you a number from like 0 to 2 raised to 32, right? Randomly a number from 0 to 2 raised to 32. Okay. So anything less than, suppose your test ratio is 0.2. So anything less than 0.2 into that maximum number will be categorized into the test set. Anything greater than 0.2 into the maximum number will be going to the train set. Did that make sense?
Exactly. Just how Gautam described it. Does that make sense?
Yeah, that makes sense. But
and this is exactly how you would choose if somebody told you to choose some numbers with probability 0.2. Then what you would do is you would sample the uniform distribution, and then you would say if that sample is less than, you'd sample the uniform distribution, and then you would require that the sample be less than 0.2, and that would, and if you do that, then yeah.
So
it's very similar.
Right. So as we are doing the CRC hashing on a 32-bit number, so that is the range on which we also need to do the test split. Like that's where we need to put the boundary.
Yeah, and that boundary that you see, that 0xFFFFF, that's one. That's 2 to the 32 minus 1.
Yes, that's right. Correct.
And so all that statement is saying really is that the hash value is less. You're asking for the hash value to be less than the test ratio times the maximum number. And every time that happens, then you throw that sample into the test data set.
Okay, I understand now. Okay, thanks all. Yeah.
Of course. Thanks everyone. Okay. So with that, and again, to just follow that, as you said, we just want to pick a unique identifier, and that's why here we can pick the index. However, we just want to bear in mind that if we add data, we do not want to change the index of that specific row. Okay, and that's why also we can use unique features. For example, here longitude and latitude of will never change, right? They're just the same. So if we actually get an identifier from these two, it's also fine. So anything, so the point here is just to hash something that is unique and that will not change when we add the data. Okay, cool. So after that, so now up to this point, we have our train set. You can see that by splitting this, we have now our test set, which is 20%, and then we have our train set, which is 80%. He also mentioned that we can do this just using the scikit-learn train test split. Above, he did it using his own function. Same thing here. We actually can specify the size of the test set, and we can also specify the seed of our random seed. For example, here 42. So yeah, so like for us guys, like so usually I would just use this, except maybe if you want to add custom things that even this function does not have, then maybe you wanna go build yours. But usually just go with that. So so now we have that. Okay.
Excuse me.
Yeah, go for it.
I have a question. Sometimes it's not a good idea to split the data randomly. How to identify it?
Elaborate more on that. You said you want to split it randomly. This is like randomly.
Yeah. Sometimes, sometimes this is a not good idea. How to identify it?
Yes.
When
okay. Good. We'll get there. Actually, that's where we talked about stratification and all that. So we'll get there in maybe like 2 minutes. And if not, and if we don't answer, just ask me again.
Okay.
So here. We have a single histogram here, and then we discuss this hist function, which is a built-in function in matplotlib that we can use. And again, last time I shared with you like a very cool shortcut that's very handy, that is just Shift Tab. You just have a short one, which this one is doing. Actually, if you press it twice, it gives you everything. And this is very handy while you're working with functions or methods from other libraries that you know, instead, for example, here I can go and type in matplotlib hist, and I will go through the documentation for that. I will just look at that here. After that, then we dealt with the categorical variable, right? That was the oh no, before actually doing the categorical one, we said that, okay, oh, let's look at this one. This is skewed here, right? We can see how this one is skewed here. And you see how, and let's make it, what we try to do, let's make it in a way that we can grab samples from all different groups, let's say. Okay, we want to grab samples from here, we want to grab samples from here, as well as samples from here. And those groups, that's what we called stratas. And how we went, so pretty much we just transformed this histogram here, which is the same one as this one here. The only difference is here, for example, what we said is anything between 0 and 1.5, we're gonna give it label of 1 and so forth. For example, anything above 6 to infinity, we're gonna give it label 5. And that's what gave us this here. And now we're actually using this to get our oh yeah, so this is here where we start to talking about stratified shuffle split. Okay, and there was a long discussion here. What's the right number of labels? What's the right number of bins? And so forth. and why actually, when is, as my fellow here just asked, when is when is it better to just randomly sample? When is it better to use stratification? And then when we said, for instance, different reasons, the first primarily one is when the data is skewed like this, and we want to like grab for the from different samples. There were other things that would hint that we should use stratified. So if anybody here, and I believe I did not look this up since last time. So did anybody look this up? Maybe they want to like share with us what they found out. And this is actually a very important thing to consider actually every time. So anybody want to share?
There is, sorry, yeah, there is a case. I think this person asked the question about when you wouldn't want to sample randomly, and there is an important use case where you don't want to sample randomly, and that is if you have time series data. Because then it's not, you're trying to predict the future, and so you need to keep your data samples in order. And what you would do is you would take a data set out to a certain time as your training set, and then you would take the interval immediately following that as your test set. And so in this case, you do not want to randomize your sampling. You want to preserve the order just as it is.
Absolutely. And to follow that, besides time series, are you guys, would you guys think of any where we would be fine, like randomly? I mean, if everything looks fine, if nothing is skewed, actually randomly is fine. But time series, yeah, time series by itself, because you know we're dealing with past data and the future. But besides time series, any other additions here? For example, here we're talking about regression, and let's just maybe stay within regression here.
I think he said in the book that that if you have a large number of samples, then you might not have to stratify. Then random sampling might be okay. But if you have a relatively smaller number of samples, then you definitely want to stratify in order to maintain samples that are similar to each other.
Yeah, that sounds good. Wouldn't you think that even large data set that is skewed, we still want maybe to do some stratification, you know?
Imbalance in data sets.
Yeah.
Yeah, so I think we got a good handle of that. So I, again, personally, I would consider this, just have it on the back of your mind, something to consider. Another very good question that came out last time, what if there isn't just one attribute that you would like to stratify based on? Maybe there are many, and that's when Joseph shared this very interesting, was it scikit-learn that they just added it lately?
Yes.
Yeah. So apparently there is a way that you can stratify based on different features and not only one. Okay.
As a rule of thumb, can we always take that stratified sampling? We can always go for stratified sampling irrespective of how large the data set is, as a general rule. Is it advisable?
So as a general rule, it's something that you would consider and that you would compare to random sampling. And that's what here Jérôme did, for example. Let's see. So what he did, he said, for example, let's go to our initial one. So, okay. So this is what we have. So here, we don't have anything special here. He said, okay, this is how much we have for label 1. This is how much we have for 5. And then what he did, he said, okay, let's compare those with okay. So what he did here, he said, let's compare those. Those were the overall ones. So those values were coming from this house in here. And then he got this test set, the third one here, from this one. This one here is just random sampling. That's why here he called it random, because this one is random. And then he compared it to the stratification test set, where he used the stratified sample. You can see this stratified test set. So he compared this with the others, and which of those are close to the ratio of this. And that's what he's showing here. So he's showing that the overall, this is what we have. And if we do just random sampling, right, without stratification, this is the ratio that we get per class or per group, right? And with stratification, this is what we get. And we can see, for example, that this one is closer to the true representation than the random sample. And that was his point that he's showing. And we can see that there is a slight one. So for instance, here, I don't think it would matter too much, you know, but it's a very good habit to kind of just be able to compare and be like, oh, okay. But still, I would still use it, you know?
Yeah, so Linda, if you look at the last two columns showing the % error, I'm assuming that means the accuracy. So it does seem to indicate that that with stratification you get a dramatic decrease in the error, even though it doesn't look too much different.
Right. Okay, I see. Yes. Very well.
Even though columns 1 and 2 don't look too much different from each other, they do have very different errors. So I would say, I mean, just looking at that, I would say, maybe it's best to stratify as a general rule, as someone asked.
Right.
Well, I'd like to also mention that I think it's worthwhile to mention that.
Yeah, Brian. Hello? We cannot hear you,
Yes,
Brian.
Okay, never mind.
No, we can hear you now. We can hear you now.
Okay, my internet's going in and out. We have a thunderstorm. So I think the reason why income category was highlighted here was because some subject matter expert, some hypothetical subject matter expert said that was a highly informative feature. So that's why he focused on this one and why it was so important to maintain the proportions. And I don't think you necessarily need to go crazy and do this for every feature, but maybe just the key ones that are informative.
Yeah, that makes sense.
Yeah,
he actually didn't have a subject matter expert figure out that the income is most important. He actually did it in the notebook. You know, in this section he showed, or the previous section, I think the one we read last week, he showed that that the income has the highest correlation with the housing price.
Yes, the only thing here is we're actually doing it before even looking at the correlation, which is. But yes, Joseph, I'm with you. If we look at the correlation and then we find the correlation, and thanks, Brian, for actually, that makes sense, right? If somebody, we know two are very much correlated, we may want to focus on that feature. Okay, so if there are no questions, I think we can then...
So then, Salim, just to add to that, would it be a good idea to do the correlation before we start doing the splitting so that we know what the important features are that we want to split up on stratifying?
So for example, I don't see a reason why not. Is there anybody that's because here's the okay. Well, actually, let's hold on. Let's pause a second. So here we're doing stratification both for training and for test set, right? But then as soon as after this, we put the test set away, right? And then even when we do the correlation and everything, we're only working with the training. Because now if we actually do the correlation and we also have the test set included, that may give us actually some clues that we don't want there. That's the only maybe thing that I see there, right?
Yep.
You guys see that with me? You see, like right now, we did this, so that way we can, after this, we're only gonna be touching the training. We're not gonna be touching the test set. So we see the correlation, but if we do, so we don't want anything biased, right? That's why I would say he did it here before actually digging more into the features.
Yeah, I would just interject that that's really important. Because training to your test set is gonna close your results. Yeah. Okay. Yeah. Okay. Thank you for that. It's good. Okay. So let's move on now. And we were looking at gaining insights. Okay. So just let's run these cells.
Oh yeah, gaining insights, and then so here kind of like the beginning of our EDA. We can still call this EDA. Really, we're just looking at the data, scatter plots of different attributes together. So we've seen that, and what this one is showing, this is latitude versus latitude, so the map and so forth. So we've seen all this. Then he downloaded an image that he overlaid, and that's what we've seen here. So and then what the result here, we said, oh, okay, yes, there is actually a relation between the location of the house and the price of the house. And then this is where we started looking at the correlation. Generally, the more uncorrelated the attributes are, the better, okay? And I think I give that example of like given one feature, but just different units, but it's really the same feature. So, I mean, that doesn't really help much. So we can see, yeah, okay. And then, oh yeah, and then here, this one here was interesting because we said we can, okay. This is just another way of looking at the features using the scatter matrix. And this, for example, this one here, what is it showing? This one, it's showing that wherever, even if I don't see this, even if we don't see this and we don't see this, and we just look at the plot, we can see that there is a good correlation between this wherever is on the x-axis and the y-axis. The x-axis is median income. Why? Because you can see that there is like an upward trend here. It's going like that, okay? So these two are correlated. And then we can actually, from different attributes here, and for example, this one, we can make new attributes, right? So,
Salim.
Yeah.
Yeah, in this diagram that we are showing the medium income versus the medium house value, there is one interesting point just I just thought of mentioning here that was mentioned in the book. So we can see some horizontal lines here, right? Something at 50,000, something like 350, 100,000, some lines are there. So they were mentioning that these are the value which are supposed to be discarded. These are like not indicative of the exact pattern. So as part of the preparing of the data for the ML model, we need to get rid of this value. You were mentioning something like this.
Yes, very well. So that's actually, so if we would to say what do we get from this plot, there are two things. Yes, there is a strong correlation between these two attributes, and there is something happening here. So there is something happening here that we want to pay attention to, okay? And that's exactly what Subasis, I hope I said that right. That's
yes.
Thank you for that. Okay. Okay. So, and then pretty much we are done. So now we'll start with, and so for example, what do you guys see? For example, let's not worry about these two attributes, but when you have a plot like this, would you say that there is a good correlation? No, we don't really see that there is good correlation between these two. Okay. So with that, we're going to start our new reading. So, and again, we'll run. You see how here I don't have the cells here, but we'll read, and if there are any cells that we're gonna run, we'll run them. So now we're preparing the data to train our model. And he mentions how instead of preparing the data, like instead of doing this manually, we want to write functions for several reasons. Primarily because you want to use maybe those transformations that you gonna write maybe on some other projects that you have, maybe on some other things, and you have those ready. And you know, it's very handy, you know, when I mean often like we just copy code from here, maybe code that we did, or maybe something that we found on GitHub somebody else did, and this and then that, and then you just put some stuff together, right? And this is exactly his point. When you do it manually, when you build functions, you can just reuse those. So that's what he talks about there. And then he says, first, let's revert to a clean training set. So here now we're gonna be using the stratified train set once again to, okay. And then he says, let's separate the predictors and labels. So we're gonna separate, meaning we're gonna, and that's what he does here. So here we have this drop. What this drop is doing is just removing that that attribute column from the data set. Okay, so now our Hessian here does not have that, and then he has, and then he copies our train set labels. So these are our labels here. He copies them to the Hessian label. Okay, so this is our labels, and this is our data set now. Okay, cool. So let's even, actually, we can just copy that. Okay, so now let's do some data cleaning. So yeah, the first thing maybe that you want to look into, are there any missing values? And that's something that we, so for example, we can come here, and then what we said last time, we said, is there any missing values? And when we actually do this, what this one is saying, it's false when there is no missing values, and it's true when there is missing values. So it does that for all the attributes. If we would like to sum the columns, then we can just sum them, and it will just tell us where are. So for example, here, total bedrooms have 150 and 58 missing values. So that's something, okay. So that's something that we want to do something about, right? So what are we gonna do with those rows, right? Okay. And yeah, and sometimes, because right now, and this is actually a fun part, actually playing around with the data. It's a fun part. It's a very important part that makes a difference even on the end goal. Like people, like I feel when we spend a lot of time learning about the data, there are some people even that they go out of their way. For example, I would get a data set. Okay, this is all that I have. They would go out of their way. They would make research about that data set, and they may find other attributes that were not included on that data set, but they believe that they are somehow related, and they would even get those into the data sets, and that would just add value to the whole thing, you know? So, so for example, here we have this, so pretty much all this data cleaning where it's saying, let's deal with these missing values, where he's saying we can get rid of them. For example, that's one way. We can get rid of the whole attribute. Do we really want to do that? We don't usually want to get rid of the whole attribute unless pretty much the whole attribute has missing values, you know, except maybe few, you know. And or we can set this these values to 0, for example, maybe, right? Because they're not available. Maybe we can set them to 0, right? And by the way, so here what we can do. Yeah. So that's something there. Okay, cool. So what he proposes here, the first option is we can drop. What's this one is doing? Option 1 is dropping. It's dropping. Oh yeah, it's only dropping this. You see how it's only dropping the 9. Let me undo that. It's only dropping the missing values. So this is good. This is actually the most maybe. This is a good one. Here, what it's dropping the whole column. And this one, what it's doing is actually replacing those with a median. Okay. Oh, actually, this is the one that it's replacing with the median. This is what all that he's doing. He's getting the median. Once he gets the median, he goes and he says, fill the not available ones with that median. That's what he's doing. Okay. Any questions up to here? Okay. If you choose option 3, you want, and by the way, here you can choose the median or you can choose 0 value. That's again something that's subjective. What are you going for? Okay, and don't forget to save the median you have computed. Okay. Scikit-learn provides a handy class to take care of missing values, the simple imputer. Okay, so let's spend some time. Yeah.
One question here. So regarding that, choosing the median as a value for filling up the NA. So is there any thumb rule, like when we choose median, there are other values we can choose as well, like the mean value, the max value. By mean, I mean MIN as well as MEAN.
Mhm.
So different values are there. So is there any benchmark or something like that when we choose median, when we choose mean?
That again comes back to the understanding of the data set. So for example, let's think of total bedrooms. What would you personally, if you have not available total bedrooms, would you personally put a 0 there? Like would you put, for example, you have this, and to even relate, think. So for example, what if I want to hear, actually, let's look at those rows. So if I want to get those rows, how can we get that's what I'm saying. So, but to answer your question, it's more your understanding. Would we want to put 0 there? Not really, right? Would we want?
Salim, there are other ways to replace the missing data. So median is just the sort of the go-to one that everyone does, but you can be more sophisticated about it. For example, you could use k-nearest neighbors to find, which of all the other data points in your data set,
Right.
the ones that are closest to this one,
Right.
what value do they have for that particular missing value? So there's other ways you can do this. It's just that the median is the go-to way that everybody does, just without having to think too much.
Okay, understood.
Yeah. Okay.
Can I, at one point,
yeah,
I think someone said difference between mean and median. I think it just depends on whether you have a lot of outliers, and if you do, then you don't want to use mean. You want to
the median is more robust to outliers than the mean.
Okay, that's a good point. Okay.
And also a good point that was made in the text is that if you do that, replaced by the median, you must remember that median value so that you can do the same thing exactly when you apply this to the test set, right? So that would be a mistake if you calculated the mean separately, the median separately in the test set and replaced it. That would be a mistake.
So yeah, going off that point, if you use something like k-nearest neighbors, you would implicitly have a lot more computation time during test, because every data set every new row you get in, you would have to do the k-nearest neighbors on that. Whereas if you're already computed the median, you can just plug and play.
Aren't we pre-computing this value just like the way
with
we
k-nearest neighbors? You can't pre-compute, right? With median, mean, and min max, you can pre-compute and hold those values. When you get a new data point.
For the k-nearest neighbor as well, can't we pre-compute on the data set that we already have, not considering the next incoming data sets?
How would you compute k-nearest neighbors?
You would have to start with the test point, with the test sample, and then as Rekil said, you would then recompute the k-nearest neighbors on the training data set and find that value that you want to impute. So every new sample in the test set, you have to repeat to the k-nearest neighbors thing. So that's why it adds the overhead that Rekil was mentioning.
I understand. Yes.
I think there is an important point to be made on the amount of data that you have. If you have a surfeit of data, if you have a lot of data, you can easily throw away some of these NaN values without it too much affecting your data set. If you have a paucity of data, then you have to essentially oversample. You have to use the median, or you have to use some other technique. Ultimately, what you would like to do is, in a perfect world, you'd create synthetic data and you would fill in things, perfectly representative of your data set. But it really just depends upon the amount of data that you have and how data hungry your algorithm is.
Okay. Yeah. So for example, you have this specific example. You have your longitude here. You have your latitude. You have the house and median age for this one is 18. The total rooms, because again, remember we're talking about these districts, right? You have the population, and then you have house, and then here you have this not available here. So based on that, So this is what's going to get replaced, either by the mean or the median and so forth. Okay, any other additions to what you guys shared? Okay. So following to that, so we were talking about the simple imputer. This is a scikit-learn way of taking care of missing values, and then here the strategy. So this is where we specify either the median or others, right? And I believe the strategy has different things that we can do there. And then since the median can only be computed on numerical attributes, you need to create a copy without the categorical, without this one, because this one is categorical. So what we're gonna do, we're gonna drop that. So we drop this one. Now our house, and that's why we have this house in num. Now we call it because it's only numerical values. There are no categories there. Okay, so let's add that. Let's add that there too. And okay, so this is our numerical one, and then we do this fit. So this fit is what's gonna compute wherever we want. So it's gonna give us this median, and then we can just get it from the statistics here. So if we just do that, if we just do fit, and then we just get that, that's gonna give us. Okay, but this is the same way if you do it like, if he does it manually, if you do it like that, and he's saying it's a good way, it's a good habit to always check between these two. Has computed the median for each attribute and stored the result in that, okay? Only the total bedrooms attribute had missing values. We can't be sure that there won't be any missing values in new data, so it's safer to apply to all numerical attributes. Okay. So now we use this transform. What's this transform here is doing? Now it's applying this, this is where we apply the replacement. So this transform is where we apply our transformation. Okay, moving on. And then the result is this numpy containing the transformed features. If you want to put it back into the data frames, we can. Okay, so let's look at this. So when we do this, what's our X here? How does it look like there? Okay, so it's just, yeah, so it's just a numpy array, and then we just put it into a data frame like that. And then it's housing transformed TR because it's transformed. Okay, so so far, okay. What we did here is we just replaced the missing values with median. Okay, and then he goes and he talks about scikit-learn design. So there are some good points here to be made. And just talks about some definitions, estimators, transformers, predictors, and so forth. And he mentions a very good paper here, which is this one, the main design principles. And I would highly recommend actually reading this just from the perspective of API design. This was published in September 2013. So a lot has been changed, but it talks about like the API design from early on. I mean, they started scikit-learn, I believe, in 2007. But yeah, so a lot of this is mentioned here. So if we just look at estimators here, exactly. So all that is taken from here. So we can just and we can just leave this as our homework assignment to kind of maybe just read through this. But you know, it's just helpful to kind of like go through this. If I would like to mention anything else, maybe to read, this is like a very nice document. And also if we just look at scikit-learn, their user guide. So this one here, which they, so yeah, it's just a newer release that was released in May 19th, but this one here had everything. But for example, if we go to the API elements, we'll find what we're talking about. We'll find everything. We'll find here descriptions for estimators. We'll find here everything. So this is also another nicer document that maybe I can share on the chat. Okay, so going over this, oh yeah, here there is this fit transform that's maybe it's important to kind of just mention it. What this one is doing is actually just doing the fit and transform and then transform. It's just combining fit and transform. And then he talks about how these transformers, for example, what we just did, the imputer is a transformer, right? Because we transformed our data. And he's talking about like how these transformers, they want to have like 3 key criterias, which are just the fit and then transform and then the fit transform. What's the difference between just to easily kind of why this, and we use this all the time. So the fit in is really, that's when we get the measurements, whatever, the median, the mean, the variance and all that. And then the transform, we just apply that to our data set, right? And then the fit transform, we apply, we actually do the fit and then the transform. And then we will ask why then do we have fit transform and then transform? Okay, let's think about it. If we have a training set and then we have a test set, we would never do a fit transform on the test set, right? We would only, because we would only want to apply our transformations on the test set on measurements that we already have from our training. So for example, we will do the fit on our training. We will do then the transform on our training. So we can just, for example, call fit transform on training, but then we will only call transform on the data sets because we want to use the same the same parameters that we got for training. And I think there is an example later on that we're going to get. If that was not clear, we're going to get to an example about that. Okay, cool. So here, since we're doing EDA, yes, we want to handle categorical attributes, which was the only one, the ocean proximity, which had 5 different ones. And then what he uses here, he uses this ordinal encoder. What this ordinal encoder is doing is it's based on the order. So it's actually encodes them. So for example, it's gonna get the order. So for example, that's the order. Let's say that's the order. So it's gonna give this one 0. It's gonna give that one 1. That's gonna give him 2. That's gonna give him 3 and 4. That's why it's this one. So it's converting these to those specific values, which is good, right? But he says that there is an issue with that because 2 nearby values are not really close to each other. So for example, here he talks about like less than an hour to the ocean is going to be transformed to, or encoded, I should say, to 0. And then here we have near to ocean, which is actually very related to this, but it's going to be encoded as 4. And we don't really want that, you know, so kind of like we want attributes that are maybe close to each other to have maybe we can have this one 0, maybe that's 1, and so forth. So with that, then he suggests another encoding one, which is one-hot encoder. And maybe if you are doing other NLP channels here and all that, or embedding things. This is very similar to embedding. So what's one hot encoder? So instead, for example, it's just one of them will be one at a time. That's all. So for example, if we're gonna go back here, and if I can write something here. So for example, briefly, one hot encoder. So this one is gonna give us, we have, let's say we can think of a vector of 5, and then, for example, let's say nearby is 1. So that will be 1, and then the rest will just be 0. And that's one hot encoder. So there can only be one hot at a time. They can't be, so if we find like one, that cannot be the case, right? So that's what one hot encoder. So we just encode these using just one hot encoder. Okay, cool. So there's just another encoding that we can use, and there's also in scikit-learn. And then we use the fit transform because this is also a transformer, right? And again, here we use fit transform, so we're actually doing the fitting and the transform of these house categories. Okay. This is what we get. Okay, these two arrays. So let's actually compile this. So let's see where we're at. Let's so we got that, and now we are here. So housing that, and by the way, token. Yeah. Okay. So and by the way, so when we actually doing it like this with 2 brackets. This is still meaning that this is like the result here is still a data frame, you know. So for example, if we actually look at the type of that, that would be still a data frame. Instead, for example, if we just do it like that, now that changes to a series. If you can also call it like this, that's also like a series. So just something just to keep in mind. So right now we're dealing with a data frame, and then we got, what did we, so we're here, right? We're here, we got that, okay, we have that, and now we're gonna apply our ordinal encoder. And it's easier to just go and copy the code from his notebook. Let's see where we are at. So we are ordinal perfect, so we are here, and if we get that, and okay, and then we have that, the categories. And by the way, so here to mention something, so these are our categories. And so sometimes, so with all these transformers, sometimes we can just, again, tab, and then we can see what are the different methods within there. So this one, we have that fit, we have the fit transform, we have our transform, we have the set parameters, the get parameters, we have these categories and so forth. And different transformers may have, of course, different methods depending on whatever was built on that transformer. Now we're gonna use our one hot encoder. Okay, so this is what he was talking about in the book. It's a sparse matrix. What's a sparse matrix? Because again, we talked about a one hot encoder. So imagine here, for example, here we have a vector of 5, right? What if you have a much larger dimension? It's not efficient to kind of like save it in memory like that. So what this one, it does, it really saves only the locations of ones. Okay, that's what's being saved. So not everything. That's why if when we get this, when we actually do the fit transform, we get this, and then we do this to kind of convert it to ND and in the array. So actually, if we want to look at what I mean even more by that, is what it's really doing is, again, this is a transformer. We can just look at what are all the different methods and all that. So it's really storing what's the non-zero. So if we go to the non-zero, that's what's being stored. So if we actually want to even look that up, So this is how it starts. So let's compare this. So you see how this is our first row. It's index 0, so it's going to be 0 0. That's why it's storing 0 0. Then, for example, the next one. So this is row, the second one. So it's 1, but it's the first one here. So it's 1 0. So it's storing 1 0, and so forth. This one, what? This is the third one, so it will be 2. But 0, 1, 2, 3, 4. So it's going to be 2, 4, and that's what it's storing. And that's how it is efficiently storing this. If we go to the last one, and then we see here the last one is, again, it's the third one here, and you can see that. So that's what he means by it's a sparse matrix, and not like a dense one. So sometimes we hear like a dense representation. Okay. Okay, let's go. But any questions so far with that? Okay, and
just one point to point out this, Salim.
Yeah, please.
Traditionally, I think in statistics, when you did something like a one-hot or dummy variable, you would actually remove, if there were five, the column had a cardinality of 5, you would remove one column out, right? You would make it like n-1, because the fifth column technically can be represented with the other 4 columns. So you would end up with like a linear dependency problem. Instead, and as far as I know, in ML, you don't end up doing something like that because you're not looking for an exact solution. You're not like inverting a matrix or anything like that. So nothing would break. Just wanted to kind of point that out.
Okay, so maybe some of the statistics fellows can talk about that. But I mean, here, for example, we have 5 categories, right? So we can see that in our one-hot encoder, there are like 5 here, right? So it's matching. Anybody else wanna answer, Raquel, or wanna add something to that? I'm not sure. Maybe I'm missing something on, or I'm not. Maybe this is what I mean. It's the same number of categories. If we have 5 categories, when we're gonna do the one-hot encoder, we do get the same. We'll talk later. There is embedding. We can actually also embed this into a different size if we would like, but we'll do something different that we may get to.
I think the author points out pretty rightly that, it can be a problem when you're converting, ordinal data or categorical data to ordinal data. You have a tendency to want to run analyses and means and statistics on them, but you can't really because it's really representing a category. So this is like a methodological flaw if you end up converting it to an ordinal and then processing in that manner.
Okay, yeah, that's absolutely true, and that's why like even me personally, I have not used this ordinal encoding before, because especially, for example, let's say, okay, we're gonna maybe just go a little bit off tangent to embedding. Sometimes, as you said, I think Stefan, he said, and maybe this is not statistics, but sometimes we want to measure the similarity between different embedding vectors, and we can do that. And that shows the relationship between the different ones. So we can also actually do that with different encoding schemes. Okay, so the last comment tip that he has here is if there is a large number of possible categories, like a country code, right, professions and all that, what we can do, this will slow down our training and degrade our performance, because if there are so many, what we want, we can replace the categorical inputs with useful numerical features related to those categories. For example, he gave this one that we're dealing with, the ocean proximity feature. We can maybe with the distance to the ocean. So for example, we can replace those categories with a measurable distance of the ocean. Okay. Similarly, a country code can be replaced by the population and the GDP per capita. So take the country code, which can be a lot of different values, but now we're going to just replace it with like, well, actually a lot of different categories, right? A lot of different categories. We're going to replace it with the country population and the GDP per capita. Only 2 features instead, so many. So that's something. Alternatively, that's what we're talking about. We can actually replace a category with a low dimensional vector, which is what we call an embedding. So even, you know, so that's something that you specify your size of embedding, maybe 3, maybe 100, maybe whatever, depending on the problem that you have in hand. And this is something he said that's going to be discussed in later on chapters, and I'm sure it is discussed.
Can I at one point?
Yeah.
Okay. I think there is a use case for ordinal variables and perhaps related to real estate data when it comes to location, and when you do know like one location is perhaps superior or inferior to the other one, and then perhaps you can introduce ordinal variables in terms of ranking the data. So
yeah, that's a good point. Yeah. Anybody else would like to add anything? Okay. Custom transformers, then he goes, oh, how about if we want to make actually our custom transformers, there's something maybe not in scikit-learn, so how, and then he goes about like he built his own custom transformer. What he's trying to do here, he is adding new attributes. So he is actually combining attributes. That's what he does here. He's combining attributes and he is making a new attribute. So for example, let's see here what's going on. So, okay, here there is not, so fit is just returns itself. So transform, so he takes this rooms, which is, so he takes this column, which is rooms, so X, by the way, so X here, when we're talking about X, what's our X? So X is our housing values, okay. That's what's gonna be called. Okay, so meaning what? Meaning if the rooms here is like, for example, 3, so he goes to that column, 3, and then for example, households, he gives it a value of 6, so he goes to that and he splits that column 3 by that column 6, and that gives him rooms per household. That's 1. He makes another attribute here. Cool, that's a second attribute. And then he says, if this specific parameter is true, then we're gonna have this added attribute. But if this is not true, then we will not have this attribute. Then we're gonna just return what we have already. Here, what are we returning? We're returning the input that we gave it. We're gonna concatenate, so this is here numpy c underscore. I think we talked about it when Joseph presented the first chapter. So this is pretty much what it's doing, is just concatenating wherever we give it here. And of course, they have to be the same size to be able to concatenate. I believe it will give an error if they're not the same size. So the original input, and then these 2 attributes that we get without the if statement. And that's it. We're gonna return that if this one is false. If this is true, we add a 3rd attribute, which is bedroom, which is this column, which is column 4. He's gonna divide that by column 3, and he gets this attribute. And you see here, he returns now 3 new attributes instead of 2. So this is the custom transformer that he built. And this is exactly, so what he said this can make our life working with this very flexible. Imagine now he only did it for 1, but maybe we can do it for as many attributes as we want. And that way, while we're working with the data, we can easily just come here and set some false, set some to true, and then we're gonna have all these attributes easily added and removed from our data sets, and we can work with them, you know? That's the whole goal of here, is of building a custom transformer. Is okay. Before going to feature scaling, maybe let's just run that, and if there are any questions. let's discuss them. Yeah, so yeah, we run, yeah, we got everything, so we are here. So he just runs that. So now he got, so let's see what's this one. So he doesn't, so let's see what do we have now so far here. Okay, let's look at it as, so it's, okay, so everything pretty much now is transformed based on this one is false, right? So meaning that we took our X and then we added 2 more features, meaning we should have had, Hessian should have had only 9 features, right? So if we actually, 9 features, right? So we had 9 features. Now that we added these 2 features, now we have 11 features, right? Because we have the 0 here and the 11. The only thing is here, you see how like we want to also like give the column names and so forth. If I'm sure if we go to his notebook, he will have the column names and all that added. So he gets that. Exactly. So that's exactly what we did. All that we want to do is we're just going to add the index and all that. Okay. Oh, okay, because he gave it that. Okay. Okay, so you see, and he called them, so these are our new ones, rooms per household and population per household. Let's actually, let's go and go actually maybe now, try to actually maybe get instead of this, only this 2, maybe let's try to see how easy is it if we want to just add this, right? He says, and then going back, he says, when we add this base estimator, right? When we add this, this is actually very helpful because from that, we can actually easily get these 2 other methods where we can set the attribute. So let's see. So okay, let's play around with this. So what are we having here? So these are what this transformer, the different methods has, and we can see that it has this set parameters, right? So I believe if we actually set our parameter to this one, because if we get, I believe we get parameters here. Oh, maybe, so we get, let's see, so that and that.
I think you might need to call it on the object, adder.
Oh, exactly, right, yeah. Okay, let's see now. Perfect, thank you. So, so yeah, so we can, so same way, we can actually set our that and just by doing this, now if we actually just run this again, we can just add the other here. Now we should be able to see now the other, okay, let's see what this one. Number, okay, must be equal. So, okay, so we did give 12. So number of manager items must be equal to, okay, so what's going on? Oh, so so we added there. So I guess we can just add it to, what did we call it? Diagrams for that. So let's just add it here. Okay, this should work. So yeah, so now we have 3 added ones. So that's all that we needed. So if we want to just play around with the first data set with only 2 attributes, we have that. If we want to just, it's just a fact of just setting here these parameters to be here true. And that's what this adding this base estimator gives us these 2 methods. This one, he mentions this transformer mixin. This mixin is what gives us that fit transform. So if we don't have this one, we do not get this. And this is what we talked about. Actually, this is something maybe to highlight here, that every transformer we want to have the fit and the transform and the fit transform. And by just giving it this transform mixin, that allows us to have that. Okay, cool. Any questions here? Okay, let's move on. So feature scaling, I'm sure you guys, we are all, maybe we hear normalization every time I feel feature scaling is just like another word for normalization. So let's just talk. Okay, so of course there are different ways of feature scaling, and then here he presents two: min-max scaling and standardization. Okay, min-max scaling is just we subtract the mean value, and then we divide by the max minus the mean. Okay, so if let's say our x, we're gonna divide, we can actually subtract our, and that's the thing. I would like to get a stylus that would make things much easier, but for now this is okay. So, and here so we have our max minus our min. So this is just, this is what he means by, so, and let's give this is our x prime, and so pretty much that's how we go from, okay, this is how we transform using this min-max scaling from x to that. Okay, and then pretty much the same way, I wouldn't really personally call this, yes, he said many people call it normalization. I would still call it min-max scaling. Usually more when, for example, and again, I mean, this is all a very good refresher for me because I haven't even done, I mean, yes, we crossed this, but not as, for example, in deep learning, usually when we do normalization, you subtract the mean usually, and you divide by the standard deviation, right? So either you subtract the mean, you divide by the standard deviation, or I now write the equation. So okay, and this is so there is another one. We will actually, and then now instead of the mean, I'm just going to represent by mu like that, and then we can actually divide by the standard deviation by sigma there. That's just another way of transforming x. Okay. What he mentions here, I believe he mentions subtract the mean and then divide by standard deviation. Okay, that's exactly what he meant. That's exactly what he calls standardization. Okay, so that's normalization. There is even another one, which is maybe like a mix between the two, and we can still subtract the mean. So here the mean, or mu. Yeah, just okay, so mu, but now instead of dividing over the standard deviation, we can divide of the max minus the min. And again, maybe a question then you may be wondering, so when do I want to use this feature scaling versus that? So this is just another one. This is actually, I mean, you would see this. So when would you use this and all that? A lot of times it depends on, and by the way, here what normalization is doing, it's shifting the distribution. Actually, it's changing the distribution. So if actually the best way maybe to actually show this is actually if somebody has a stylus and want to draw a distribution and they want to show how like a distribution can be changed using this, for example, here, the mean would be 100, but because, for example, we're going to subtract the mean, our mean now is going to be 1. And then when we divide by the standard deviation, no matter what the value of the standard deviation was before, now our standard deviation is going to be just 1 unit. And that's what he said here, as a unit variance. Joseph, did you want to draw something here? Okay, maybe Joseph is not here. Okay. But you
yeah, sure. I have to figure out how to do this for a sec. Let's see. Advanced sharing options. Let's see. I guess there's a way to do a stylus on somebody else's screen, and I did that before, but now I can't see how to do it.
Okay. Okay, that's fine. So what I'm saying is, let's just think of, okay, we have we have something like this. This is not really, we would not call this a normal or Gaussian distribution, but after normalization, this, for instance, and forget about the mean being 0, this actually would just be, and that's what we're looking for, okay? And for example, here, usually what we talked about, so for example, here, let's say this point here is 100, right? But using this feature scaling that we did, we're going to shift it. So actually it's going to be now, instead of being there, it's actually going to be here. You know, and just don't worry about this, the drawings, but it will be like centered around the mean that will be 0, and like the standard here deviation would be, for example, 1. Anybody, please, would like to add something to this? Maybe something that I skipped over or I didn't mention?
Yeah, I'll just draw another distribution that, suppose you had something like this, a distribution like this, and then you applied what they call normalization in the book to it, and what that does is it shifts it, you know, it shifts it to be wherever you, it shifts it to be wherever you, I mean, I guess it shifts it to be between 0 and 1. So the new distribution would be shifted to be something like, you know, it would look like the old distribution, but now it would be between 0 and 1 instead of between A and B. And of course the you know, the area under the curve would be the same, although I haven't drawn it that way here. But yeah, that's what normalization would do. It would map some kind of distribution with fixed endpoints to a new distribution with fixed endpoints at 0 and 1.
Yes. And if I would like just to add something on to what Joseph said, and we can specify sometimes, you see like how here it's 0 usually, it's 0 and 1. If we want like another interval for some other reason, maybe that we're looking, we can also actually do the feature scaling based on whatever interval we're looking for. So yeah, if there is a reason for that. Okay, any other addition up to this point? Thank you, Joseph.
Yes, one point I want to mention here is that, so basically for feature scaling, what I understand, one of the main thing is to reset the distribution. So if the distribution is skewed at some point, then take it to around some median value or something like that. So we are applying the formula x minus mu by sigma for that. At some point of time in the book, I don't remember exactly where, but in the previous class only, I saw that they are mentioning, in the book they mentioned that for the same purpose, they are going to take logarithm of the thing. So have you heard about applying logarithm for doing this thing, apart from that formula, the generic formula that we go through, like x minus mu by sigma? They just mentioned applying logarithm.
For normalization, I don't see why you would apply a log. Does anybody have an idea why?
More so they were mentioning for feature scaling, I think.
It doesn't cross anything. I don't see like a reason why I would why there would be a use for log here, but maybe if somebody else have crossed that.
Yeah, if I may add, I think the standardization won't actually make your distribution normal. Like if you have skewness, the skewness will remain. So if you want to actually make something normal, if you want to change the distribution to normal, then log is something that might help. Like log of the variable might will actually reduce the fat tails, and it will try and make it more normalized.
Right,
Whereas standardization won't make it normalized. It
specifically
will
they
just,
were mentioning, as I remember, they were specifically mentioning for this column that median income. So if you see the scatter plot of that one, sorry, the histogram of that one, you will see it has a long tail. So for getting rid of that one, probably they were mentioning that.
Yeah, so log of large values will just, I mean, you will just get a smaller value, right? Since it's logarithmic, yeah.
Yeah, I think so. That in general, the prescription is if the data has a large dynamic range. In other words, if it spans many orders of magnitude, then it might be good to take the logarithm instead.
So would you do it? Would you do it 2 steps? Would you take the logarithm and then subtract the mean and divide by standard deviation?
You would, let's see. Yeah, well, yeah, you would want it to be standardized. So you'd first take the logarithm, yeah, and then you'd work with the logarithm, and then you would first subtract the mean of all the of the logarithms, and then divide by the standard deviation of all the logarithms. It's just the same way you did with the ordinary data.
Okay, thank you. That's interesting. I never thought of that. Thanks.
So going back to your point, do you prescribe that for large dynamic ranges or for long tails? Because
I'm thinking large dynamic ranges, but I guess long tails could also be a good application.
So Joseph, I didn't understand one point. What is the difference in intention between applying the logarithm and doing that formula like x minus mu by sigma?
Okay, so if you have a data that has a lot of that spans a large dynamic range. In other words, the data might go from 0.01 up to 10 to the 5, right? So you have data of all different sizes. But if you take the logarithm, then that puts everything between -2 and 7, right? So
Okay.
you've basically shrunk your data set into something more manageable, and then you could use that, data as your starting point, and then standardize it or normalize it, right?
Okay.
Yeah.
Okay, so basically, as I understand, the purpose of logarithm is to shrink the data range, and for the standardization intention is to standardize the location of the distribution.
Yes. Well, standardize the location and the width.
Width, right? Okay, understood.
Okay. Thank you, Joseph, for that. Is that clear to everyone? Any other questions? There is just one last part that we're gonna go over.
Sorry, one quick question. Isn't the purpose of standardization also relative to all the other columns that you want all of them in the same range? That you don't let one particular column hugely influence things. That's another reason you do the standardization, is because you want all
Thank you
of
for
your
that.
data points to be in the same range.
Thank you for
Yes.
that. Yes. And Joseph, if you can just take off, please, the drawings now. I think there's.
Oh, thank you. Yeah. Thank you for reminding me. I'll do that.
So thank you for that. So that was a very good point. Exactly, and that's what Jérôme he says here. For example, look at this range from 6 to 39,000. That's like one of the attributes has this range versus like another range that is only from 0.15. But when we're gonna apply the standardization or normalization, they're gonna be both within the same range. Okay, so and that's that is important. Okay, thank you for that. So the last part now, I mean here we are at the training, so we're almost done. But this part here is important. What we did, so you see like how now we worked with numerical ones and we worked with categorical one, and then we did different steps in our transformation. For example, what was this imputer? You guys remember with me? What was the imputer doing? We used it to fill out those missing values with the median. That was like processing one. Another processing we added here. Remember we added new attributes. That was like another pre-processing step. There was a third one here, right? We were just talking about now, the feature scaling. So all this, so he puts them into a pipeline, and this is this is built in on scikit-learn, that we can just specify all this, and we're just gonna go through them, and we're just gonna apply the fit transform to all of them. The fit transform to all of them, meaning that it fits and then transforms that. So it fits the median, meaning what? Meaning it gets the statistics for all of the attributes, then it transforms the data set, then it goes to the next one, it fits here, and then it transforms, except, and he says here, all but the last estimator. All but this last one will only just apply the last one must be, they must have, when he says sequentially, and so there reaches the final, which only calls the fit. So the last one is only calling the fit method there. Okay, so that's what a transformation pipeline is doing, and now we can just call it like this, and then when we call this fit transform on this on this pipeline here, and this is our data set, and then it just applies it to all the steps. That's all that he's saying here. And then he talks also about this new thing that apparently they just added in scikit-learn, which actually combines now numerical and categorical. And I believe in his first edition of the book, he had it differently. This is something that he added on this new edition of the book, because it was just, I believe, made available in scikit-learn. And this one here, so we have our numerical attributes here, and then we have our categorical attributes, and we have our pipeline, this one here that we just did here, right? Our numerical, this is numerical pipeline that we just did. So we do that first here, and then we add our one-hot encoding of the categorical ones. And now this is what he calls the full pipeline. And now we can just call the full pipeline, and it will call the fit transform on the numerical, and then it will call the fit transform on the categorical. So I believe here we had like maybe 12 features total or something, or 11. And then here we had 5 or so. I believe here we had like 11, and then here we had 5. So the total should be 16. So actually, if we go, we can just go to his notebook, the result, and that's what he did. So we don't exactly. And so the final shape after getting everything together, we would have those 16. So this here, they would include those encoding of our categorical attribute that we did. And that's the 16 where that one's come from. So that's what he did here, and we can just run that. Up to that, really, that sums it up. Anything that sums it up. Now we're here. Anything? I believe we are already. And thank you guys for staying with me. Whoever is here, thank you guys. I know it's past 8:30, so thank you for sticking around. But I'm here to take any questions or just discussion or wherever you guys still have any doubts about or something. And here, by the way, that's it. Actually, we are pretty much done with the core of the chapter. All that he talks about now, he's like, okay, let's call the regression model. And then he calls like linear regression. That's the beauty of scikit-learn. It's just like 1 line, 2 lines. That's it. You call your model, and then you fit it, and then here you have the result, and then you can just predict on it. And you can do the same. It's kind of, and that's the consistency that they mentioned in the API. They're actually doing everything the same. So they have the same thing for linear regression. We just call it like that, and then we do the fit. Once we did our fit, we're really actually then we're really to just predict. We just have to specify the data and labels, and then we're really to predict. And then he does that for linear regression, and then he says, oh, well, linear regression is really off. Like the results are really off, and then he applies the same. He's like, okay, well, let's find a better model. Actually, what this one happens to be doing, it's underfitting. And I believe maybe if chapter 1, we talked about underfitting, but we'll review all this, but this maybe it's a good point maybe to stop here. And then he tries other models like decision trees and so forth. And then lastly, he finds that they're still doing bad, and he says, okay, let's fine tune our models. And that's kind of like what we're gonna talk about Sunday, and just wrap all these, wrap up all this. So yeah, so any questions or anything? Okay, guys, well, again, thank you. And I really enjoyed it, and I enjoy it every time. And you have a good rest of your day. And if there are any questions, just post them later on the Slack. And then Joseph, thank you actually for looking up stuff after the session and responding. That's also very helpful.
Yeah, I thought that Friedman-Diaconis rule was really interesting, because I've been working with histograms for many, many years, but I've never seen that before. And it gives you a principled way to choose the right bin size. It's just really exciting. So have a look at that if you're interested in that.
Yeah, actually, yeah, I have it pulled up here. So, so with that, have a